we've seen some examples of similar matrices. We haven't seen anything on like how to decide whether or not two matrices are singular. Um, all we've seen so far is these are some examples of matrices that are similar to each other. Um, and we got a sense for what that means with respect to uh, representation of linear maps and all that good stuff. So the next logical step would be identifying, um, well, identifying when you can say that some easy examples of matrices are similar to each other. So let's start with this first example, where we'll talk about the easiest matrices to understand, which are the zero matrix and the identity matrix. So the question that I want to start with is this: what matrices are similar to the zero matrix, and what matrices are similar to the identity matrix? Let's start with the zero matrix. Okay, so let's say that B is some matrix that is similar to the zero matrix. So that means that it's equal to P times the zero matrix times P inverse. Well, then right away I can say, because I'm multiplying the zero matrix times some other things, keep in mind that P and P inverse have to also be square matrices of the same size as the matrix in the middle that you're multiplying by. But anyway, it doesn't matter so much. What matters is that if you multiply a matrix by the zero matrix, you get out the zero matrix. So this product over here is equal to the zero matrix, and so B is equal to the zero matrix. And therefore, the only matrices that are similar to the zero matrix are, well, is the zero matrix itself. So the zero matrix is only similar to itself. Okay. What about the identity matrix? So if, let me use, let's say like M for this one. If M is equal to P times the identity times P inverse for some invertible P. Should have written this in the last example, but I didn't. I was sloppy. I'm sorry. Anyway, so if I multiply by the identity matrix, I just get back the same thing. So let's multiply like P times the identity first, and that's equal to P. And I'm left with P times P inverse. And this is equal to the identity matrix because, you know, they're inverses of each other. And so the only matrix similar to the identity matrix is the identity matrix itself. So the identity matrix is only similar to itself. Same sort of behavior as the zero matrix. So that's one weird quirk about this. Keep in mind that we've already seen examples of matrices that are different from each other, like, but they are similar. So not all matrices are only similar to themselves. The zero matrix and the identity matrix are kind of special in that regard. But anyway, here's another question I want to look at. So let's suppose that A is similar to some matrix B. Is it true that A squared is similar to B squared? So we could, if we had no idea where to start with this problem, maybe we would start by computing some examples. Maybe we would take the 2x2 example that we talked about at the end of the previous video, and we would take our matrix A that we started with and square that, and then also take our resulting matrix, which was equal to P times A times P inverse, and we could take that matrix and square that and see if we're getting the same thing. that would be a perfectly fine way to start exploring this question on your own. And the more you do it, the more that you kind of convince yourself that this looks like it should be true. And so why is it true? Well, I'm just going to go through the proof of why this is true. So the answer is yes. And why would that be true? So let's say that A is equal to P times B times P inverse for some invertible matrix P. So I want to say something about A squared and B squared. So I want to show that A squared is equal to like Q times B squared times Q inverse for some invertible matrix Q. How might we go about doing that? Well, one thing you might think about doing is, well, you can, to get A squared showing up in this equation, I could just square both sides. And so let's see if that does anything for us. So we'll square both sides. So on the left, I just get A squared, of course. And on the right, I get PB P inverse squared. Can I simplify that? Well, let's expand it out and see what we get. So if I expand this out, I get P times B times P inverse times PB P inverse again. And here in the middle, I have P times P inverse. And so those cancel out. That's equal to the identity matrix. And I'm left with P times B times B times P inverse, which is P B squared P inverse. And again, that's equal to A squared. That's what we started with. And so A squared is similar to B squared. So the answer is yes here. Let me back out. I'm not able to scroll. Okay, here we go. All right. So question. Does this work for like A cubed and B cubed? What if I ask this question for like A cubed and B cubed? How would this change? Well, you could instead cube both sides, and then over here you get P B P inverse again, and then what happens here? Well, let's see. So you get P inverse here, P inverse here, and so these would both cancel, and we would just be left with P times B cubed, because we would have this B, and this B in the middle, and then P and P inverse on the outside is all equal to A cubed. So this would also work for if we cubed both sides. So A cubed is similar to B cubed. And this holds for any power. So if A is similar to B, then A to the n is similar to B to the n for any positive number n. It actually also works for any negative value of n. You would just do the same thing, just using inverses. The only difference there is that, well, if you're going to do if you're going to have negative powers in there, then all of a sudden you're assuming that your matrix is invertible. So assuming that A is an invertible matrix, then this also works for negative powers of n. And of course, it also works for A to the 0, because A to the 0 is equal to the identity matrix. And the identity matrix, A to the 0, would also be similar to B to the 0, which is equal to the identity matrix. So any matrix is similar to itself, especially the identity matrix. So it works for that as well. Okay. Here's an observation. Let me not scroll too far down. So if A is equal to PB P inverse for some invertible, let me scroll down so you can see it. For some invertible P, then A and B are matrix equivalent. So remember, our definition for matrix equivalent was that A is equal to P, B, Q for some non-singular P and Q. And here, A and B had to be the same size. P and Q had to be square matrices. A and B didn't have to be square matrices, but if we're talking about similar matrices, then everything does have to be square. And so the idea with matrix equivalence was that you could, think of P and Q as doing row and column operations respectively. And we said a lot of things about that. We were able to classify matrix equivalent matrices by their rank. That's something we talked about. So similar matrices is a special example of this, where my Q is just equal to P inverse, the inverse of our non-singular matrix on the left here. So similarity is a special case of matrix equivalence. So similar matrices are matrix equivalent. And with that in mind, I want you to think about how you would go about proving this next example. How do we show that these two matrices are not similar to each other? So A is equal to this upper diagonal matrix. It's in echelon form, I should say, rather. And it has 1s along the diagonal, 2s along the off diagonal, and then 3 in the top right corner. And then B looks like this. I have 1, 1, 4, 0, 1, 9, and then a row of zeros. So think to yourself, how would you prove that these two matrices are not similar? I recommend pausing the video, coming back, seeing what you figure out. Okay, I'm going to move ahead. So, all right, how do I do this? Well, the idea is we can use this above note. It might be easier to just show that they are not matrix equivalent, and therefore, if they're not matrix equivalent, then they couldn't also be similar, because similarity is like a special case of matrix equivalent. Because if they were similar, then they would also be matrix equivalent. So let's show that they're not matrix equivalent. Well, one thing we talked about before was that A is matrix equivalent to B if and only if the rank of A is equal to the rank of B. So I could just say what the rank of these matrices are and claim that they're not matrix equivalent from there. So the rank of A is equal to 3, and the rank of B is equal to 2. So 2 is equal to rank of B. 3 and 2 are not equal, so the rank of A and the rank of B are just different. So A and B are not matrix equivalent, and hence also not singular. Sorry, not similar. Hopefully I didn't say singular too many times in these videos as well. But yeah, so that's it. Keep in mind, this is not always going to work. It's very easy to come up with examples where A and B both have the same rank, but they are not similar matrices. But if you have two matrices where the rank of one and the rank of the other one are distinct, then that's like an easy way to check that they are not similar and that they're not